Uh, it's showing up. Okay, so the first thing I'll do today is just to finish off this alternating series test. And then I'll start telling you a little bit about Taylor polynomials as a motivation for power series, which is like the next topic we have to discuss. So let me see. Let me start by sharing my screen. Okay, so last time we were talking about the alternating series test. So this is a series where like the terms alternate between being positive or negative or negative and positive. So like the examples that I had given you were like -1 to the n over n, right? Where like say if you start, oh, let's say n plus 1, where if you start at 1 to infinity, that's kind of like 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc. Or another one, just an easy one, would be something like -1 to the n over n squared, uh, which would be minus 1 plus 1 over 2 squared, uh, minus 1 over 3 squared, plus 1 over 4 squared, minus 1 over 5 squared, etc. Okay, so the this type of series that we want to analyze, what made them alternating was that, as you see here in this pattern, they switch between positive and negative. So let's say A. If the coefficients change sign, right? Like if the terms alternate from positive, positive to negative or negative to positive. So it can start either positive or negative. That doesn't matter. Now, in practice, what we need for like the alternating test to work is that we require two more things. The first one is that the coefficients, or like the numbers that you're adding in the series, they start decreasing in absolute value. So for the alternating series test, we also need so there are two more things that you need. That the terms you're adding, the terms in absolute value are decreasing. And not only are they decreasing, but their limit should also be going to 0, because that's required for like nth term test. If you remember, for a series to converge at infinity, the terms that you're adding have to be going to 0. So moreover, the limit as n goes to infinity of a sub n equals 0. So if those two things happen and the series is alternating, then the alternating series test says the series converges. So in this case. Okay. So hopefully no one sit there just in case. So is that okay? So what I'll do is kind of like explain a little bit of the idea of why it works the way it's supposed to work. Um, because applying it in practice is just like literally identifying that you have an alternating series that meets this criteria, and then you're good. You can say that the series converges. Okay. So it's more like a recognizing the series as alternating whenever you want to use a test. But it's still useful to understand a little bit of why it works the way it does. Okay, let's just hope that it doesn't like. Oh, okay. If not, we'll maybe. Okay, and perhaps we should do a small. Okay, let's just do another like 2 more minutes, and if not, we can just transfer like the day of the exam to. You think like what if we just transfer? Okay, so like I'll just pause like here. Like you made it. I turned it off. No. Okay, let's. Okay. Okay, so five. Let's wait 5 seconds. If not, um. Okay, so for now, let's assume that this continues. Okay, so why does this work? Okay, so the idea first, I'll draw pictorially like the situation that we're in. So like let's just imagine that the first coefficient started being positive. So this is kind of like the tower that I drew last time. So like imagine that the first coefficient is positive, right? Then the second coefficient has to be negative, because if the sign switches, and also has to be slightly smaller, right? So I think that kind of looks smaller. Then the third coefficient is positive again, and it has to be smaller than the previous two, right? Then the other coefficient is negative again, right? And it's smaller, and then this one is it's even smaller, and it continues like forever, right? So this is kind of like an accurate, representation of what's going on, and the series is kind of like adding all these heights together. If you think about them as towers. So okay, and we're doing like kind of, you know, we're considering A1 minus A2 plus A3 minus A4 plus A5 minus A6, etc., etc. Right? So here, just to make it easier, I'm kind of like putting the sign in front of like the number two. So like here, I'm thinking like A1, A2, A3, A4, A6 are all not are positive, and then putting like literally the sign in front of them. Okay. So like a series converges, right? Like the criteria for convergence of a series is that the limit of the partial sums exists, right? So we have to study the limit of the partial sums. Okay. So the first partial sum is just S1, right? Is what we had called before S1, which is just the first term, right? There's nothing else you can say about that except that it's going to be positive because like way I started the series is with a positive term, right? So this is just some positive number, right? Now the second partial sum is A1 minus A2, right? And there's not much that you can say here, but if you look at the picture, just to kind of like zoom out a little bit, if you look at the picture, since A2, like in absolute value, it's a little bit less than A1, this difference, right? Like this one is positive, you're subtracting another number, which is positive. So like this sum altogether is less than the previous one. Okay, so whatever this sum is, it's like the only thing that we know is just that this is S2 is less than 1. Okay, so this one is less than the first one. That okay? So far, so good. Now, I will just do two more, and hopefully that will show you where the pattern comes from. So if you do S3, right? What is S3? That's A1 minus A2 plus A3, right? So there are two ways to think about it, right? One way is that this is this is a little bit, this is the sum of the first two terms, right? Is S2, right? So this is just S2 plus A3. Which is kind of like how the partial sums work, right? Like the next partial sum is like the previous partial sum plus a new term. So if you look at it from that perspective, this third partial sum is a little bit more than the second one because now you're adding like a positive number, which is like in the diagram what's going on here. Um, and so this is a bit higher than S3. Sorry, this is a bit bigger than S2. But here's okay. So that is a bit bigger than S2, but it's still less than like the original sum because if you look at it, S3 is also S1, right? This is also S1 minus A2 minus A3, right? And so because the numbers are shrinking, this is some positive quantity, and then you're subtracting a tiny, like maybe a negative number from like the first sum. So this is so what that means is that S3 is going to be less than S1. Okay. So I'll just, oh, sorry, yes. Oh, the thing is like the way I'm sorry, like maybe the picture how I drew it is here when like when I'm writing the sum, like the series this way, I'm explicitly, maybe the picture is a bit misleading here because I'm thinking like, like the idea is like in the, as you were saying, like the alternating series test does assume that the heights are shrinking. Like so this one is kind of like the tallest tower. This one is less tall, then this one is less tall, then this one is less tall, this one is less tall, and so on. So they're like, that's otherwise it wouldn't, like, this wouldn't work. So you're kind of like assuming that they shrink in size. And here, when I'm writing A2 minus A3, I'm kind of just looking at the heights. So like, I'm assuming that I'm referring to their positive point, like their absolute values, if that makes sense. So yeah, otherwise you wouldn't be able to say that. So so for example, the way this is starting to look like, I don't know if you remember, like I'll maybe show you like the GeoGebra animation from last time, but the way this is starting to look like, if you look at the partial sums on where they're being labeled, so this is the value for the first partial sum. Okay, what can we say about the second partial sum? The second partial sum was less than the first one, right? And then the third partial sum, what can we say about the third partial sum? It's less than the first one, so it should be to the left, but it's also bigger than the second one. So it's actually kind of going to land somewhere in here. Okay. Okay. And just to do sorry, this should have been the third one. Oops. And just to do one more, like to show you how like the pattern is, like, I don't want to give like a like full argument, but then the last one would be A1 minus A2 plus A3 minus A4. So that is the third partial sum minus A4, right? So that means that because you're subtracting a tiny positive amount, that is a little bit smaller than S3. So less than S3. Okay. And kind of because the heights are decreasing of the towers, it's actually a bit bigger than S2. So it kind of like ends up landing somewhere in here. And that kind of like the pattern kind of like goes on forever. So like S5 is somewhere here, S6 is somewhere here, S7, So what ends up happening is that S5 is somewhere in here, S6 is somewhere in there. So kind of like the partial sums are kind of like approaching a fixed number somewhere on the number line, okay? Which would be the limit as n goes to infinity of S of n. And that's why like the partial sums have like a convergence. They converge to something. And again, like it's, I'm just trying to give you like some idea of like why it ends up working that particular way. Like the details, in practice, we can just use it the way we want. So that is why the kind of like the partial sums, that's why like the limit exists. So this is why. Makes sense, kind of. And okay, so and in practice, as I was saying, like the usefulness of this uh test is that it does cover cases that you can not use before. So like the best example is like the alternating series of 1 over n. So this one, because of like the alternating series test, it would converge. So this one come here in absolute value, a sub n is 1 over n, which is decreasing, right? And the series alternates. So by the alternating series test, it converges. So. And the nice thing about this example is that this is an example where if you put if you had tried to check whether there's absolute convergence, this one would have failed. So there's no absolute convergence for this one, right? Notice that there is no absolute convergence here. Since what is absolute convergence? Where you put absolute values to the terms, right? Since this thing in absolute value diverges. And that is kind of like the last definition about all this convergence, divergence stuff, which is conditional convergence. So you say that a series converges conditionally if it converges, but not in absolute value. So that's kind of like the last definition before moving to like the next topic. But so let me write it down. So uh, we say that the series converges conditionally if the series converges, but not in absolute value. If the series converges, but there's no absolute convergence. But there is no so in other words, that with absolute value, the series diverges. So I don't know. Yes, what it says, questions about this. So, like again, in a sense, like absolute convergence is the best you could get because if you have absolute convergence, then the regular series converges without absolute value, and conditional convergence is kind of like a somewhat good situation because at least without absolute value it converges, and the worst thing that could happen is that both diverge, right? So like maybe to make it as a table, so with absolute convergence, both converge. And with conditional convergence, only the first one converges. So um, convergence, convergence. And when you say that the series diverges, right? And we just like divergence. Oh no. Okay. I'll finish writing this and then let's move. So let's switch to the one like two rooms to the right. And I actually this is like the last thing about series. I now I'm going to move to the Taylor stuff. So it's like at least a somewhat decent place to start. Okay, so I'll try to see if we can move permanently. This classroom is kind of cursed. So there's something that happens like every like with so let's just move to the other side. Oh, I mean, is that the projector? So and I was like, oh, do we have another? And it was right next to us. I just didn't know it would be so such so much, you know. Oh, I mean, but I'm sure that we can just get this one back. I'll just, but yeah, we can like project and project. Okay, perfect. Now we can continue the recording pause. So let's just switching topics. So at least we ended up at a good spot because the next topic is Taylor polynomials, which is actually kind of like a nice topic. So and it's a least more simple than what we have been doing. So I'll talk about this today, the remaining minutes that we have, and then I'll lay it out for motivation for what we're going to do next. Um, so just as a quick reminder, a new topic. Let's put it here. Uh, so what is a polynomial? So a polynomial, so a polynomial is just like a combination of like terms like x squared, x cubed, x to the 4, right? A polynomial is, well, polynomial of degree n, let's just say. So for example, a degree 3 polynomial, right? So degree 3 polynomial. So like the combination would be of like 1, x, x squared, and x cubed. Okay, so a polynomial is any of these terms multiplied by a number or and then all being added together. So like a polynomial could be something like uh, 2 times 1 minus 3x plus 1 times x squared let's say minus 4x cubed, which you would just then write as 2 minus 3x plus x squared minus 4x. So I mean, I'm writing it in this way to kind of like emphasize that you essentially take like these quantities, which are called monomials, like like different powers of x, and you choose your favorite numbers and just like combine them together. This is actually what's called like a linear combination because you just multiply the numbers by like the terms by constants before adding them together. So if you ever have to take linear algebra, it's the same sense in which they talk about linear combinations. So like in general, like a degree n polynomial, right? So like actually let me put it here because otherwise this slide is going to kill me. So a degree n polynomial is something like polynomial is like a constant term, which I'll call C0 plus the terms C1x plus C2x squared plus C3 x cubed plus up to you get to Cn. Cn x to the n. Okay, which with the sum notation, you can write more nicely as saying this. And the CKs are just different numbers. Like they are supposed to be constants. So like CK, each CK is a number. Yes, sorry.
CK kind of like their own series?
Uh, well, if right, like next step will be Wednesday, where we want to take a limit as n goes to infinity, right? And then you could think of like the CKs as making up a series, correct? Yes, yes. And then this will be called like a power series. It's kind of like a limit of polynomials in a sense. Yeah, yeah. But that will wait for not for a moment. I will motivate this in a slightly different way. But yeah, like that is one approach that we will take later, like next time on Wednesday. Just like to think of like because the moment is the thing is like once you have like the coefficients that pretty much determines the polynomial, right? Because of the convention that they are just like the different powers of x. So was there someone else who wanted to ask me? Were you going to ask me? Or were we good? But yeah, like that's correct. That's why I'm using like a notation that's kind of like setting it up so that it looks very similar. I'm just using here C's for constants, just to emphasize, oh, it's a constant times a power of x. Otherwise, I would have called this A, A sub k, but like C for constant, yeah. Just to make that a little bit more clear. Okay, so now why are polynomials useful? They are useful because in a sense, most realistic functions can be approximated by polynomials, and that has to be made more precise. And that's kind of what I'll start telling you about today. So the idea is that polynomials are nice since I'll put that in quotes, like that's kind of like the statement that in mathematics, then you worry too much about making it more precise, but your friend, like the friendly functions that like they can be approximated by polynomials, and we'll kind of like study how to do that. Most functions that you have studied. Okay. So the first approximation of this sort that you have seen before is Calc 1, the tangent line. Okay. So what is a tangent line? So let's start with that. So just to make the problem a bit more concrete, imagine you have the graph of e to the x, right? And I want to find the tangent line to the graph at the point 0, 1. Okay, so here's the point 0, 1, right? There's a tangent line there. Um, what is the equation of a tangent line? Is y equals mx plus b, right? So this is y equals mx plus b. The b is easy to determine in this case because like that should be, like the point like the line should pass through the point 0, 1. So like that's the intercept with the y-axis. So it's just mx plus 1. The harder part, and that's where you actually need calculus, right, is to find the m. The m is like the first derivative evaluated at that particular point, right? Well, we know that y, like that's the nice thing about the exponential, right? Is its own derivative, right? So like y prime of 0 is just e to the 0, which is 1, right? And so that just gives you x plus 1. And I'll write it just so this is a polynomial, right? This is a polynomial of degree 1, which I'll just write as 1 plus x because I'll do more approximation. So it's better to start with the constant term first. So this is kind of like a polynomial, which is 1 plus x. And the 1 here just means that you are doing degree, it has degree 1, the polynomial. So this is like a degree 1 polynomial. That okay? So far, so good, everyone waiting up to this point. So, right, so the line is kind of like a tangent line is kind of like an approximation to the graph of the curve, to the graph of the function using a degree 1 polynomial. But then like it's like a natural thing to ask, okay, why stop there? Like sometimes other types of polynomials can be useful. Like, for example, parabolas are important things, right? So you could try to ask, okay, can I approximate the graph of e to the x with a parabola? Okay, so like here comes like the next question. So next question. Now you want to approximate the graph with a parabola. Let me see if I can move this. Sorry about that. Okay. So what is like a parabola in general? So first let me try to draw the picture. So what I'm trying to say is that maybe here I had the graph e to the x, and I have like the parabola, which if you had to draw, like for example, if you had to draw a parabola, right, that approximates it, like here's a bad choice. Like, and we'll explain in a moment why it's a bad choice. This would be a bad choice for approximation. This one looks a bit better, Why does this one looks a bit better than the other one? Because the concavity, this is a concave up parabola, right? And if you remember, what is the second derivative of, well, that's a nice thing about the exponential. Like the first derivative is e to the x. The second derivative is e to the x as well, right? So e to the x is always positive. So this is always concave up, right? So if you were to try to approximate the graph with a parabola, it does make sense to try to approximate it with a concave up parabola. So I'll try to draw like the approximations like this. Okay. So far, so good, everyone with me. And kind of like in the spirit of like the sequences where like when we talked about these recursive definitions, it would make sense to, because okay, first this is supposed to be a parabola, right? So like the equation of a parabola is y equals ax squared plus bx plus c, right? I'll rewrite it in the notation that I want to think about it. This, like, so usually that's how you refer to a parabola, but it's kind of like better to switch the name, like the names of these constants to what we were saying. So I'll write it as C2x squared plus C1x plus D0 so that we know how to generalize it. So I'll write this as C2x squared plus C1x plus D0, C0. Okay. And the parabola has degree 2, so this will be a second degree polynomial. And so the way in which I'm going to, and I should have used like a different color here, but the way in which I'm going to find it is that the second polynomial, like the parabola that approximates this, should be the first polynomial plus an extra term. That's what makes the most sense, like kind of like as a recursive definition. So the way I'm going to try to find it is that the second degree polynomial that approximates a curve will be the origin, like the degree one polynomial plus the new thing. And the new thing is C2x squared. Okay, so that is like the extra term that you're adding because this is like the quadratic term. Okay, so far so good, everyone with me? Okay, and then to determine, like we already know what P1x is in this particular case, right? It would be 1 plus x for this equation. So let me just put here 1 plus x. So the question is how how should you find this coefficient C2, right? Once you know C2, you know the entire parabola, right? So I will find it by asking the second derivative of this polynomial to agree with the second derivative of the function at that particular point. That's what will make it approximate the best. So like if you look at it, like just to go back, the tangent line, what makes it the tangent, like, what makes it the tangent line is that, the first derivative of the function, which is just one, agrees with the first derivative of the exponential at that particular point. I mean, almost by definition, like of how the tangent lines are computed. And so kind of like to go with that like idea, the second degree polynomial should match the second derivative of the function at that particular point. Yes.
Is that just because we have like the rate at which the slope is changing, so like both the parabola and the properties?
I mean, it's just like, it's kind of almost like applying like well, like it is like like the most natural condition in a sense because right, it's kind of like how much like if you imagine like if you had approximated at a different point, if you had approximated at a different point with a tangent line and at a different point with a tangent line, how much would those tangent line approximations have differed from one another? That would have involved like a rate of change of the slopes, and that's kind of like a second derivative. So that's why you would require the second derivatives to match in that particular case. So because yeah, like if you imagine like um that there's another tangent line here and another tangent line here, you could ask like how are the tangent lines changing as you vary the point, and then that would involve like the second derivative. So that's where it comes from. But even if you don't think about it from that perspective, it does kind of make sense that it would match like the second derivative just because it is like a degree 2 polynomial. So like the concavity, it's like another way of saying like, okay, you want the concavity to be the same, right? And the concavity has to be equal, it has to do with the second derivative. So you might as well, that means that at least they should have the same sign, both be positive in this case. But why not as well make them agree if you already want the signs to be the same? You know what I mean? Like that kind of pins it down. So we are going to require, so we will require that the second derivatives match at x equals 0. So in other words, so the second derivative with respect to x at 0 should be the second derivative of e to the x when x equals 0. Yes.
So with these approximations, we try to get, is like one of the things that we assume. Is one of the things that we assume, one of the conditions that we try to make it like more, our approximation really accurate, like around zero.
Right, although you can do it around another point, and I'll write the formula in a second. It's just like a shift. So, if you kind of like, if you know how to do the approximation about 0, you kind of know how to do it anywhere else because you just like subtract, like you kind of do like an overall shift. I'll explain it in a moment. But yeah, like there's nothing special about 0 here. It's just like certain numbers are just easier to evaluate at 0 than anywhere else. But like there's like a formula for approximating it somewhere else, and it's basically the same idea. It's just like, instead of like x, the thing like here, it's like x minus 0. The other formulas would be like x minus x0, where you're approximating somewhere else. Okay, but now what is the second derivative with respect to x? Like this doesn't count because like it will go away, right? The second derivative of a linear function is 0. So you only have to worry about taking the second derivative of this part, and like the second derivative here is the 2 comes down, so you get 2c2x, and then you take another derivative and you get 2c2. So you would get here 2c2. And what is the second derivative of the exponential at 0? It's e to the x evaluated at 0. So you get that c2 equals 1/2. So the polynomial that approximates the exponential in this case would be 1 plus x plus 1/2 x squared. Oh, because is it okay why this second derivative is 2c2? So that is okay. So this is, you wanted the second derivatives to agree, right? So let me write it in a bit more detail. So what is the first derivative of p2? It would be if you look at this formula, right, it would be 1 plus 2c2x, right? And what is the second derivative of p2? Like this goes away and then you just get 2c2, right? Is that making sense? And you want to force this to agree with the value of the second derivative of the exponential at 0. And that's why I started with the exponential today, because like its derivatives always continue being the same, so they're super easy to evaluate, right? So the second derivative of the exponential is e to the x again, and at x equals 0, that gives you 1. So you get 2c2 equals 1, right? And that's where the c2 equals 1/2. Is that okay? Okay, so let me just show you how this started to look like before I do the next term. And once I do the next term, you'll see that where the pattern comes from. Okay. So do I have it here? Oh, okay, perfect. So this is e to the x. This is e to the x. And okay, this is like a very contrived way to write this, but this is just 1 plus x, essentially. This is 1 plus x. Then the degree 2 polynomial is with n squared. Okay. And so again, this is like looks terrible, but it's just like it's kind of gives like the formula of how it's supposed to generalize. But this would be 1 plus x plus, you see 2 factorial is 2, so 1/2 x squared. So it now looks like this. And if you did a degree 3 polynomial approximation, what would happen here? So we'll find it in a moment, but now this is how the approximation looks like. And you could imagine going forever, like, to like add more and more terms. And I don't know if you like, keep track between like the green curve is the original function. The red curve is like the approximation. And so you see like the difference between them kind of like becomes less and less in a sense, which has to be more precise. You would like to say that this in the limit gives you a series that converges to the function. Like that's kind of like what you want to say. But we are still not there, but that's where we're headed, right? Okay. I'm almost done, so I'll just kind of write like the formula for the exponential, then I'll tell you where this is headed next time. Let me see if I can disconnect this. Oh, did I use the cable option? Sorry, let me share with the cable. Yeah, so I'll just do like the degree three case explicitly, and then I'll tell you how everything else is supposed to work. So for degree 3, right, you would like to approximate the graph by a cubic. That's what a degree 3 polynomial is. So case of degree 3. So the polynomial, again, it's kind of like a recursive definition. So like the polynomial is supposed to be the previous polynomial plus a cubic term because that's like the new contribution. So like we already have the degree 2 polynomial. So that is 1 plus x squared over 2. And now we're just trying to figure out what this new constant should be. And the condition would be that the third derivative of this polynomial will match the third derivative of the function. So the condition will be that the condition we're after is that the third derivative about this. I'll just write the prime notation one more time. Uh, prime should be the exponential, like third derivative of the exponential when x equals 0. Okay. But again, just to do it quickly on the aside, what's the first derivative? The first derivative is, well, you have this expression. It's 1 plus x plus 3c3 x squared. The second derivative would be 1 plus 6 c3x. Okay. And then the third derivative would just be 6 c3 6c3. So that tells you that 6 times c3 should be, what is, okay, this is going to be e to the 0 again, right? Because the exponential is its own derivative. E to the 0. So that tells you that c3 equals 1/6. And so the degree 3 polynomial would be 1 plus x squared over 2 plus x cubed over 6. Okay? Yes.
Why would you- triple derivative when obviously we just wanted the concavities to.
Oh no, right. But the thing is like, the concavity, has because you want to make successive and the thing is like the features of the graph, they're not just determined by the concavity or like the first derivative. Like if you wanted to know all the features of the graph, you actually need to know all the derivatives. So it's just that for most practical purposes, like the first and second derivative already give you like a pretty good idea of what the graph is supposed to look like. And so the idea is that with the linear function, the most you can determine is the first derivative. With the quadratic function, which is a parabola, you can go up to the concavity. And with the cubic, which is what we have here, you can go up. That doesn't have like any particular name, but whatever follows like the feature given by the third derivative, which you don't name anything specific, But like the third derivative also has like a geometric interpretation because it's like the rate of change of concavity. Like what is that called? Like no one gives it a name, but like but it's just like, the point is that once it's cubic, you can kind of match the third derivatives, which is kind of what you're trying to do, and that will give you like a better looking graph. And then what you want to do is now write this in a way that's a little bit more convenient to generalization. To do that, you can realize that 6 is 3 factorial, then 2 is 2 factorial. And so you get, let me write it like this, 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. Okay. I'm almost done. So like the idea will be that since, and this is something easy that you can, I mean, not too bad that you can check, but hopefully this is kind of, um, convince yourself that the nth derivative, what is the nth derivative of x to the n? N goes down, then n minus 1 drops, then n minus 2 drops, then n minus 3 drops, so you will get n factorial. Once you know that, this is where like the formula will come from. So like the approximation of degree n to the exponential is up to x to the n divided by n factorial. So for e to the x, so for e to the x, the degree n polynomial that approximates it, is the sum from xk equals 0 to n of x to the k divided by k factorial, which is what I was writing right here. So 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial up to x to the n over n factorial. Okay. And what we will start discussing next time. So next time I'll kind of like write like a formula in general, if it had not been like just like e to the x, how would this look in general? But kind of like a goal for us is like in what sense, right? In what sense could you say something like that this should be like a series, right? Well, like usually people just write this with n at this point, just to make it nice. Sorry, x to the n. Oops. And for something like the exponential, it is more or less true that this is kind of like in the way that you would expect it, that the limit of these partial sums is e to the x. This will be called like the Taylor series for like the exponential. And that is where like you get all these funny looking formulas. Like for example, if you take x equals 0 here, if you take x equals 0 in this formula, you would get that or let's take actually x equals 1, which it's nicer. If you take x equals 1, you get e to the 1, which is just e, right? So you would get that e equals 1 over n factorial, the series, which is actually true. So that's the type of thing that we have to analyze. So what I'll do next time is kind of like give you like the formula for the degree n polynomial that approximates a function, and then we'll start talking about what happens when you start taking this type of limits, and you will end up with something that's called like a power series. So we'll start discussing that. But this is a good place to end. So let's end here, and I'll tell you some more about all this stuff on Wednesday. And I'll try to see if we can officially move to this room. I think there's not an issue because no one has classes here, so I'll send an email and then I'll remind you. Bye. Yeah.
Okay, I'll
Oh, did you make that request or? No, it's just that I forgot to look at them, so I wasn't very, you have, oh, yeah, but you can show me if you want. Oh, yeah.
I know you.
Oh, okay, so yeah, I'll give you the point, just like, yeah, just make that request and I'll change it. Were you going to ask me something?
This.
Oh, that just meant the n derivative of x to the n. So for example,
See you later. I'll have you.
okay, yeah, it's kind of like better in this condition. The x double prime is 2, then x cubed triple prime, like the third derivative, then would be 6, which is 3 factorial. Then the fourth derivative of x to the 4, 4 factorial, right? And then the nth derivative.
It's just gonna be n factorial.
Yeah, it's like I'm gonna write n prime here, but yeah, it's like n factorial. Yeah. Because like you see, every time it drops down like an exponent. So like every
You're multiplying like.
right. Yeah, exactly. Yeah. Correct. Yeah. Sure.
This will probably, oh, sorry. At the bottom, when you say gold. like, just
In what
every-
sense this is true? Like that's what we're going to discuss.
And the answer is.
Yeah, it is true. Basically, like as a limit, like the limit of this as n goes to like the limit of the partial sums for any x converges to e to the x. That's what we like will make more precise next time. Uh-huh. Uh-huh.